Come back. So, in this class, we have been discussing electronic testing, and so we started by discussing what is the importance of testing. Then we went into digital testing. So, digital testing. So, there is a lot of digital logic in modern SOC, right? You may have microprocessors, you may have microcontrollers. The CPU is an example of a digital building block. Okay. We have also looked at other building blocks like ALUs, um, then maybe barrel shifter. So we will have all kinds of digital logic, right, inside the SOC, memory controllers, a DMA controller. All these are examples of digital logic. And when we were talking about digital testing, we talked about fault models. So remember that we distinguished between a fault and a defect. A defect is a physical phenomenon such as a transistor being permanently open or permanently closed, a dust particle, or a short between VDD and one of the lines. Whereas fault is a manifestation of the defect, it affects the logic. And the fault model that we looked at is the stuck at fault model. Okay, in particular the single stuck at fault model. So we have already looked at this. So the single stuck at fault model was popular, okay, for many years as the only fault model. But somewhere in the 90s, right, other fault models made their way into testing. Okay. See, aluminum was the first metal that was used in VLSI. Right? Aluminum is a metal that was used. It is a cheap metal, right? But when the complexity of the circuits increased, right, and the interconnect resistance became higher because of the length of the wire being long, right? Uh, in order to sort of bring down the resistivity of the wires, they shifted to copper. So aluminum to copper transition took place in the 90s, right? And when they make wires, right? See, remember there could be many layers. Okay, there could be many layers. See, when I draw a wire, if I try to wire everything in one plane, right? Sooner or later I will get into block situations, right? So let us say I have created all these wires. Okay, so maybe I have a gate like this, and I have to connect it to this gate. Okay, and I have another gate here, and I have to connect it to this gate. You will realize that this wire is blocking it. Okay, so I will not be able to use the same plane. Okay, So I'll have to create another layer. And usually what they do is vertical uh, wires are placed in one layer, and horizontal wires are placed in another layer. So I could do something like this. So this is vertical, horizontal, then the vertical is like this, and horizontal is like this. And if I want to bring in another wire, this is horizontal, vertical. So there will be no, this is not a short circuit because they are on two different layers. Okay, but when you have to shift from one layer to another, you will need what is called as a via. So the wire will have to go from one layer to another layer. Okay, so this is known as a via. Today it is common to have more than two layers. Okay, in the early days they used to have two layers, but now it is possible to have many layers. This is true both in PCBs as well as in VLSI circuits. Okay, so if it has to go through many layers, there will be many vias. So there could be some wire which is in this layer and then changes layer here, changes layer here, changes layer here, and so on. So these vias help you to climb from one. They are like small staircases you can think of. Okay, see, I may be in a big building, so if I have to go from one floor to another floor, I have to walk, find the staircase, climb up, and so on. Okay, so this is sort of like a small staircase you can think of it. So earlier we used to worry about faults in the wires, right? The wire could be open, or it could be shorted to ground, or it could be shorted to VDD. Two wires can get short circuited and things like that. Okay. So when the complexity of the wiring increase like this, right? So when the circuit complexity increased, that means more gates and more wires. Okay. There may be in, sort of billions, okay, millions and billions, right? Then it is something people wanted to know whether it is enough to use only stuck at faults. Okay, so stuck at faults, which have always been very popular and continue to remain popular, may not be adequate. So other fault models are needed. Okay, so an example could be, say, take these two circuits. I may have a circuit like this. When I lay out this circuit as a CMOS logic, then these wires could be running very close to one another. And as a result, they may short circuit. Okay, see, these two wires, they are not supposed to short. Okay, this is output of, let us label this as 1 2 3 4. this is the output of gate 2, this is the output of gate 3. If they end up getting short circuited, right, then the circuit has a malfunction. Okay, and unfortunately circuit fault may not completely explain that. Okay, when these two guys short circuit like this, can we say one of them is stuck at one, etc.? Be difficult, right? So this fault model is known as the bridge fault model. Okay, so two wires which are outputs of two different gates are shorted. So suppose I have this output is X and this is called Y, then X at Y means X is bridged. So when does it pose a problem? It poses a problem if the two outputs are different. Okay, if X is 1 and Y is 0. Okay, so suppose I apply a 0 1, then this output will be 1. Okay, and this output will be 0 and this output will be 1. Okay, so there is a gate which is trying to pull this to logic 1, and there is a gate that is pulling it down to logic 0. Okay, these two wires are different wires. Okay, there is no connection between them. But if they get bridged by mistake, okay, then you can see that this NAND gate is trying to pull the output to 0, whereas this guy is trying to pull it up to 1, and there will be sort of a tug of war between X and Y, and one of these wires will win. Okay, and we don't know who will win. That depends on the relative strengths of the transistors used in the two gates. So it's possible that X will win the race and they will both become one, or it could be that Y will win the race and both of them will become 0. It's possible. Okay, so that is what is called as a bridge fault. So we refer to AND bridge and OR bridge. So AND bridge means X at Y, a fictitious AND gate gets introduced, and X at Y OR bridge means a fictitious OR gate gets introduced. Okay, so let us explain this. Okay, in our example, this is what our example was: A, B. Then we had NAND gates. If there is an AND bridge between these two guys, it's as though there is a fictitious AND gate. So X and Y are feeding a fictitious AND gate, and that output of the AND gate feeds both these guys. Okay. The effect of bridge between X and Y is that this fictitious gate gets introduced. It could be it could also be a bridge which is OR bridge. So in that case, it will look like this. A fictitious OR gate that is feeding. So let us understand the behavior of these two. Okay. So in this example, this will be AB bar, right? The output of the first gate is AB bar. The output of the second gate will be A dot AB bar bar, which we can simplify. A dot A bar plus B bar, which is A bar is 0, AB bar is, okay. So we can simplify this as A bar plus B. And by symmetry, this guy will be B bar plus A. And this output will be A bar plus B dot B bar plus A bar. So if you simplify this, you will have A bar B bar, B bar will be 0, A bar will be 0, and AB. Okay. If you further simplify, this will be A bar B bar bar dot AB whole bar. So that can be written as A plus B and A bar plus B bar. So that can be written as A bar is 0, A bar B plus A B bar plus B bar, which is 0. So this is the logic that a good circuit will produce. So let us call that Y. If there is a bridge which is an AND bridge, we have already seen what X is. X is A bar plus B. And Y is A plus B bar. Okay. So these are getting ANDed here. And that is being inverted. See, when the same input goes to both the inputs of the NAND gate, this will be the output. So let us call this Z. So if you simplify, this will be AB plus A bar B bar, and you will notice that it is very similar. So this AND, if there is a fictitious AND gate between these two, unfortunately the good and the faulty circuit will behave identically. What about this? Okay, we know that this is equal to A bar plus B, and this is A plus B bar. Now this will be the sum of the two. Okay, that will be what? 0. Okay, A bar plus B plus A plus B bar will be 0, and the output will be 1. So if there is an OR bridge between the two wires, the output will be 1. So why which was expected to be this, is different now. So bridge faults can result in faulty behavior, and sometimes they don't. Like in this example, even though there is a bridge between the two, they seem the AND bridge will sort of not reveal the fault. Okay. So bridge faults, the reason why they are important, right, is that they are distinct from stuck-at faults. We cannot model them as stuck faults. Okay. Take another example. Suppose these two guys get bridged, okay, A, B, and C. Then we don't know how this circuit will behave. This may oscillate also. Okay. The output is bridged to input. Okay. So it may behave like a sequential circuit. It may oscillate. So when you have bridge faults, the behavior is so bridge faults are distinct from stuck-at faults. What does it mean? If you only do stuck-at fault testing, right? If you only do stuck-at fault testing, then you may miss the bridge faults because there is a distinct difference between stuck-at and bridge faults. So we need test tools or test pattern generation tools are needed for bridge faults. Okay, these are different ones. So the stuck-at fault ones will not work. So let me take a small example. Very simple example. A good circuit will produce AB dot C plus D. Whereas if there is a fictitious AND gate between these two, AND fault between these two, okay, or AND bridge between these two, this is a good circuit's output. Whereas with the fault, it will be AB dot no, AND bridge will produce the same thing, right? Whereas OR bridge will produce something different. Okay, OR bridge will produce something different. AB plus C plus D, right? So E will be AB and F will be C plus D. The fictitious OR gate will produce this, and the same output will go to both of these guys. So G will be this. Okay, this is the faulty circuit. Let us call this Y prime. So we have to apply A, B, C, D in such a way that y and y prime are different. Okay. So what might work? Okay. Suppose I put A equal to 1, right? B equal to 1 and C and D equal to 0. Then what will y be? C plus D will be 0, so y will be 0. But here AB will be 1, 1 plus 0 will be 0. Okay. So if I apply uh, 1, 1 here and 0, 0 here, a good circuit will produce a 1, a good circuit will produce a 0 and 0. Okay. But if there is a fault, which is here, then the OR will cause both of them to become 1. Right? The OR gate will cause both of, and this will become 1. So A, B, C, D equals 1, 1, 0, 0 is a test vector for E at F. Okay, that means a bridge fault between E and F. Is that clear? So today uh, it is common practice to also test for bridge faults in addition to the test for stuck-at faults, single stuck-at faults. Okay. So you can see that the complexity of testing has gone up. Okay. There was a time when only stuck-at faults were considered sufficient, but now in addition to stuck-at fault tests, we also apply bridge faults, bridge fault tests. Okay. You may argue that, look, I mean, in this example 1100 was a test vector that we figured out. Okay, maybe we would have used 110 for some stuck-at fault also. Okay, so if that is the case, then we are happy because the same stuck-at fault test would have also tested for this bridge fault. So if there is any common test between the single stuck-at fault and the bridge fault, we don't have to apply them twice. We can apply only one of them.